time for part 2 of reverse engineering this pirate arcade Nintendo board. And in this part I'll go over how I came up with a little device to get a UART into this system so I can actually probe all the chips on the board and turn things on and off and see how that works. And I'll show a schematic of this, how I assemble it, how I tested it, bugs I found, how I fixed them, and then finally how to use a logic probe to debug a circuit board like this. And I'll show the little drawing I made of how everything is connected. It took me about two or 3 hours to fully reverse engineer all the mapping hardware on this board. There's, I don't know, 40 some chips on here. It didn't take very long because everything's all in patterns, and I've done this so many times, so that's what you can expect. Okay, I'm going to do the build of this little circuit board right here. So what I have done, I made up this little circuit board. Here's my EEPROM that I pulled off of that arcade board, and I got a little ribbon cable, and it terminates with a little plug here that'll fit into the socket. And what I'm going to do is get the board here. So here's our board. I'm going to actually plug this into the socket like so, and this will let me get my UART that I'm going to mount on this board and hook up. This will let me get my UART in here, and I'll write a little bit of code and put it on my own EEPROM. And then this will let me hook a serial port up to here, and I'll be able to actually probe the chips and everything all live and figure out how everything works. Sort of kind of like a miniature version of my copy NES, only it'll be a bit more general, and I'll be able to use this reverse engineering just about anything else that has an EEPROM or WRAM on it. So that's my idea, and we'll see how well it works. If you want a convenient way of doing this, all you do is just plug your strip socket into your chip and then cut it off here. That way you don't have to count these. There. So now my handy dandy UART is socketed, so it will go on the board, say right here. Like that. And I left enough room in here so my wires can route between those two chips right here. And maybe I'll give it one more space. It's not really terribly critical. And then what I'll proceed to do is I'm going to have to connect all the wires from this ribbon cable to this EEPROM, and I'm just going to run them from here to here, here to here, here to here, over and over until 27 out of the 28 are connected between these 2 points. So that directly connects the pins of this cable directly to the EEPROM as it would be in the circuit. And then what I can start doing after that is tapping into the signals, and I will make a selector that will enable this UART and disable this EEPROM for one small segment of the memory, so I can get my UART into the CPU space and actually be able to read and write it. And I wrote on the whiteboard what I'm about to do, so before I go any farther, I'll actually explain that. Okay, so what's going to happen here? Here's our EEPROM as it exists on the arcade board. Is connected between A0 to 15, so there's 16 address lines here. We got 8 data lines, and then we got our chip enable, which is running on the board to that programmable logic device, that 44 pin part, and then output enable just grounded. So what I'll do is I will connect all 27 of these pins except chip enable directly back to the socket where they came from. So all I really am interested in is this chip enable. And what I will do is I'll have this whole circuit here, and the way the circuit works, I have a 74HC688. This will connect between A8 and 15, which are the upper 8 lines, to the A side, and the B side will connect to this dip switch with pull-up resistors, and the dip switch is grounded. So what this will let me do is this output will go low when A8 through 15 equals what the dip switch is set to, and this will allow me to map that UART anywhere in the address space in a 256 byte slot. So I'll probably map this as, say, 5200 hex, but I could map it anywhere. And then so when A equals B, this line goes low, it will enable our UART right here on this chip enable. And so the UART, when this goes low, will actually be sitting on the bus now, and then we got this NOR gate, NOR gate, NOR gate, and what this will do is this will disable the EEPROM when this is on. So when this is on, the EEPROM is off, and vice versa. So if this line is low, this line will go high, because this is a NOR gate, so this is an inverter. So this will be low, this will be high, and so this is a NOR gate also. So this output will mandatorily be low because this one is high, because we're a NOR gate. And then we got yet another inverter, so this output will be high, turning off the EEPROM. So when this pin is low, this pin will always be high and the EEPROM will always be off. Now let's say this is high, meaning the UART is turned off, so this will be low, so this will be high, depending on the state of this now. So if this PLD line is high, this will be high, low, high, and the EEPROM will be off like usual. Now if this PLD line goes low, they'll go low, and since this is also low because this is high, this output will go high and low here, and then our EEPROM will be turned on. So if this goes, so if this is high here, then since this is a NOR gate, this output must be low, and so this will be low, and then this will be high, and our EEPROM will be off because that's an active low chip enable. That has to go low for that EEPROM to turn on, and since it's high here, it's not going to turn on. So now let's say, get rid of that. So now let's say that PLD line goes low now. So that goes low here. We're disregarding this for now. So that means this will be high here, and this will be low here. So basically the signal just flows straight through and turns EEPROM on. So that's how that works. Now, if this line here were to go low, because our UART is on, this will be high here. And since this is high, this is going to be low here, and then this will be high again. And that EEPROM's not going to turn on no matter what. If this goes low, this is still high, so the output's not going to change. So this is basically what amounts to an active low AND gate. And I just used a 74HC02 because that way I only needed one chip. I could have used a 74138, a 74139 selector to do this, but I thought the NOR gates would be just the easiest way to do it. I'm using 3 out of the 4, and that is the idea. So, as I said earlier, here's our 63A50 UART. It's very, very simple. It needs a chip enable, a read-write, the data lines, and the address bus. I haven't drawn those. And we just get transmit and receive data, and that'll connect through a level translator or whatever to my computer's serial port. And then here's our oscillator here that I was talking about. So this will be 19.2 kilohertz at this point here. And this will drive our transmit and receive clocks, and that's how we're going to set our baud rate. So this is the game plan, and now I will wire up that oscillator on my actual little circuit board, and then we will test it and see if it works on there, and if it does, I'll continue wiring the board up, and we'll actually try it out. My power supply is actually running, so if I hook up the ye olde scope probe here, I need to ground this, so I'm going to just grab another wire here and ground my scope probe. And I should see, when I put my, yeah, I got you can see that very easily on the camera, but I have a nice square wave there, and it is 38.3 kilohertz. So I should be poking around here. I should be able to find like 19.2 kilohertz, which is going to be, say, so here's 300 hertz. So if I want 300 baud, I can get 300 hertz. There's 600 hertz, 1200 hertz, 4800 hertz, and there's 19.2 kilohertz. So I think I'm gonna go with 19.2 kilohertz here, just for fun. Let's look at that oscillator. Oh, look at that, it looks like a sine wave. So, and it's reading 4.91 megahertz, which is exactly what it should be. So the reason I'm used this particular crystal, I have my little selection of crystals here. I keep them in this little blue case here. I mean, I got all sorts of things. I got a lot of oscillators here, regular crystals, little baby crystals, resonators, you name it, I got it in here. And I poked around and I found this little can crystal here. It's a 4.9152 megahertz crystal. And the reason I chose 49152 megahertz is because 4.9152 megahertz divided by 256 happens to be 19.2 kilohertz, which is the exact baud rate I need. Imagine that. So, and this 4060 is a 14-stage binary counter, so by tapping the output number 7 or 8, depending if you start from 0 or 1, that will be the 49152 divided by 256, and that gave me 19.2 kilohertz, and we saw it on the scope, and that's exactly what I got. So that tells me that this chip is actually going to work, my crystal works, and my circuit works. Okay, I spent about 2 hours and stuffed my board here, so now I have this little board. And this has the 74HC688 8-bit comparator, my two little rotary dip switches here that have hex numbers around them, the EEPROM socket, the UART socket, and my little oscillator are in there now. And I had to move the wire on my, had to move the wire here on the oscillator because I really needed the 16x clock and not the 1x clock, so I really needed 307 kilohertz instead of the 19.2 because I read the data sheet and it said that for the 1x mode you have to synchronize the clock and data externally, and I wasn't about to do that. And then we got the 7402 and then my connector that connects to that socket adapter. So I can do a little close up here, and I had these wires that's powering the board through the socket because I was testing my oscillator after I redid it. And then these are little dip switches right here, and it's kind of hard to see, but I set the dip switches to, actually I had it on 41. It's kind of hard to see that. And so those two switches there will let me set these two switches will let me set the address where this UART is mapped into memory. So I have it set at 41 right now, so the UART will be mapped in at 4100 hex, and nothing is there, so this UART shouldn't affect anything. But what I'll do first, I'll take this O2 out, the quad NAND gate, or the quad NOR gate here, and then I will connect a wire between the input and output of this. So pin 1 is the output, and then this is the input right here from the header, I believe. Chip enables right there. 3, 4, 5, 6. And it looks good. So if I pop this EEPROM on the board, the original EEPROM here, like that, and put the header on here, this little connector, and then plug it into my board like that. It's kind of hard to plug in because the cable's in the way. So there, my little adapter board is now plugged in to the socket on the circuit board, and my EEPROM is in this socket. So the next step is going to be to make sure everything's hooked up right, because I'll test all this stuff first. So 3, 4, 5, 6, 7, 8. This would be D0, I believe, and it is. Then D1, D2, D3, 4, 5, 6, 7, and then A0 is going to be here, and A0 I believe is what, pin 4, and then A1, 2, 3, 4, 5, 6, 7, and then 8's on the other side of the chip, then 9, 10, then 11, then 12 is back on over here, 13, 14, and finally 15. And then ground, and then power. And yep, everything looks like it's all connected. So theoretically, this board should boot and function again. So I'll set this all back up. Okay, so now I got the board set up, and sure enough, it's working just fine with its surrogate EEPROM board right here. Get that a little farther on the screen, and the video quality on my monitor here is a lot nicer than it was now. It actually looks decent. That's because there was the C22 here. The video coming out of pin 21 went through C22 into all the circuitry to decode the video. So I took C22 off for the moment, and now that unloads pin 21, so now the video amplifier is working properly and our video looks good. So I can, if I can find my other clip lead here, oh, here it is. Still has a resistor lead on it. I can put some money in here. Like that. So now the screen looks quite good. So now if I'll select, say, game 11 there. And sure enough, it works fine. So that means the next step will be to make a new EEPROM, and I'll probably skip showing how to do that because you've seen me in the last video do the dumping, and that's not much different. So what I'll do is I will put my monitor code in here, plug this UART in, and put this NOR gate back in. Actually, before I do that, find my NOR gate. I will put it back in the socket there. So I got my NOR gate here, and I got my UART. So I will turn this off and plug these chips back in, and it should still function properly. Like that. Plug the UART in there. Yeah. So now I got the UART in, this in, and then this connector plugs into an adapter I have that has an FT232 in it, and then this gives me my serial port. So I got transmit, receive, and ground on those 3 pins, so that'll run to the serial port. And my socket doesn't want to stay in. Now I'll fire it up again, and it should still work. And sure enough, it does, and it looks like my PVM is acting funny again, like it was a while back. I don't know why it's doing that. There's something wrong with the monitor itself. So it seems to be working properly with my chips in there. Too bad my monitor is going tits up, but what can you do? So I'll cut here after I modify my doodad, and I'll put it on an EEPROM, and what I'll do is I'll put my code on here, and then I'll put some other data in the top of that EEPROM, so I'll be able to find that EEPROM when I start dumping data through the serial port. I'll be able to tell where this is mapped, and what I'll be able to do is I'll write to the registers and see what happens, and we should be able to, when I write to those registers, watch the outputs here. I'll get out the logic probe, and we'll be able to actually see the bits turning on and off on these 2 latches when I write to them, and also to this audio enable over here that's coming off of this CPLD. Well, I got my board fired up here, but for some reason it's not seeming to want to communicate. So I had the old scope out here. I'll put the camera on the scope a bit, like that. And I was poking around here, and I was looking at the signals on the EEPROM, and it seems to be working properly. this pulse here, this is the enable to the UART, and it's every 96502 clock cycles, and this tells me that it is polling the UART, trying to send the data back to the PC, but the UART isn't letting it. It's just saying it's busy all the time. So I was looking around, and it's possible that this CTS line may not be in the right place, or there's also this clear to send line. If that's not, I think it's supposed to be low, but if it's supposed to be high, that would explain it. Right now it's low, pretty sure. Yeah, see, it's low right now, and this carry to detect thing's low also. And then receive RTS is 5. It's low too, so the UART's saying that yeah, it's okay to send. And I can actually see the data coming in when I actually try to communicate from the PC. If it slows down like that, and then I actually try to communicate, you can see the data right there coming from the PC. So I know the receive is working. And that clear to send line, or the receive pin 5, doesn't seem to do anything. It's just kind of stuck low. That's an output, so I would pretty sure it's an output. Yes, that's an output. So I'm not sure why it's not actually sending anything. So I know my EEPROM is working because I can see the code running here. It's pulling that UART enable line pretty well. So I am not sure yet. Well, I know why this wasn't working, because I totally forgot to hook up the two control signals. This UART here has a write line and it has a clock line. So those don't come out of the EEPROM socket here, so they connect on these two pins of the UART. So I have to manually connect them with some wires. Orange is read-write, so read-write connects to pin 34 of the CPU. So pin 40 of the CPU is right here. So it'll be 498764. So this should be read-write, and so the orange wire goes on read-write, and M2 comes out of pin 31. So that'd be 321. So that's right here. There. And no, that's not farting, that's my chair. I've got a new chair now because my old chair was crap. And that now like that. And now our read-write line should be properly connected this time. I guess I'll turn the monitor off. Oh yeah, the monitor decided to fix itself right before I changed the EEPROM on this. So we're in 41. The UART is indeed connected, so I'll plug in my serial cable here and turn the power on, and if I'm lucky I will see it say OK, and it does. So now I am connected in through the serial port to this to this arcade board. So now what I can do on the computer, I can actually probe this and see what happens. And I guess I can, actually my ground wire broke again on my little stupid little video mod here. Fix the soldering on that. There. I can hook the audio or the video up, and as I can poke the PPU, and I should be able to turn the screen on. So let's turn the PVM back on. I will turn on the screen by poking the PPU control registers through this, because it is indeed working. Yes, it is. Oh, and now it's screwing up again, but earlier it worked fine, and now it's bad again, so I really don't know what's wrong with that monitor. Maybe I'll do a tear down and open that monitor up and see if I can figure out what's wrong. I'm guessing it's some kind of intermittent or similar problem. Okay, so to turn the PPU on, oh, and now the PVM is working fine again. That whatever's wrong with it went away. I tried multiple video inputs, it still does it, so I'm really not sure what's wrong. Okay, so to turn the PPU on, you write 18 hex to register 2001. So when I do that, here, let's see, we're going to poke address 2001, and I'm going to write 18 hex to 2001 here. And cool, the screen came on. So that's telling me that everything is working on my cute little board here. My code and my EEPROM's working, so now I can poke and peek anything on this board. So what that'll let me do is I'll be able to poke all these registers now. So I'll get out the logic probe. So here's my logic probe. It's a Micronta digital logic probe. It's actually a Radio Shack logic probe. This is like the only good product Radio Shack ever sold, or so it would seem. So I'll clip my positive lead on here. So we're at TTL mode. So now what I should be able to do is I'll be able to figure out where these things are mapped. Okay, that's 80 hex. So if I write 0 there, it should go low. And it does. So IC16 is port 5001 hex. So same with like bit 0 here. So if I write 1 to there, this should go high. And it does. So that's telling me that this is 5001. So this is probably going to be 5000 or 5. I'm guessing this is 5002. So let's find out. So I'll write 1 there. Okay, we already got 1 in there. So I'll write 0 in there. Yep. So I wrote 0 in there. Now if I write 1 back in there, it should set that bit again. And it does. So now every time I write to this line should pulse. So I'll put this on pulse. So every time I hit enter over here, or click the mouse button, so we're actually writing. So IC15 is 5002, and then this is 5001. So 5002 isn't doing anything. So if I change that to 5001, now it works. So these two are our control registers, and I spent some time the other day and actually drew out most of the schematic for all of this important multiplexer circuitry. It took me about 2 hours to trace all of this out, and come to find out, let me get this off of the board. Come to find out, this is indeed an MMC3 like I thought. And this is an MMC1 clone. I thought the MMC1 was 28 pins, but I forgot. It's actually 24. So I checked the pin out of this chip and an MMC1, and they're identical, pin for pin. So this is MMC3, MMC1, and then these two 161s over here are just like on a regular NES cartridge. This one is AN-ROM. So it's got 3 bank bits and then the mirroring bit, and then this one and this are a UN-ROM. It's a 74LS32 and then the 161. So you got UN-ROM, AN-ROM, MMC1, and MMC3. And then these 74153s here, there's 4 of them, select between these 4 mappers. So these 4 chips are what actually select which of these 4 mappers controls these program ROMs here. And then so these control bits run those selectors, so whatever you write to these chips sets all the hardware for the mapping up. So 2 of these bits control if you're going to get AN-ROM, UN-ROM, MMC1, or MMC3. So all the menu software has to do is just write to these 2 control registers, and that selects the proper bank that the game is in. It selects the proper mapper and sets the mirroring up. And so all they have to do is just reset it, and then the game will just run because everything is all set up now. Okay, here's what I drawn up. It's a little schematic of these are all the multiplexers on the board. And it's kind of hard to see because this is just like a really quick drawing. But this is a 1 page, and this just shows how some of the mappers are all hooked up to all those are all multiplexers there. And then here's page 2, these more multiplexers, and actually this here is the AN-ROM, this is the UN-ROM, and here's its OR gates, and then here is another multiplexer. This multiplexer is multiplexing the IRQ signal, and then the chip enables from all the mappers. And then finally, yet more multiplexers, and these are what actually drive all, as you can see, these drive all those ROM upper address lines. So like these are like character A10 through A16. Then we got this chip here. This is at 157 near the top of the board, and this is actually controlling VRAM. Controls the chip enables, output enable, and the write enable on the VRAM. And then this IC16 bit 6 here controls high is going to be this RAM is disabled, and low it's going to be this RAM is enabled, and then that also kills this here, which is selecting which of the four the character ROMs are going to be used, and 16.6 here comes in here and it's a positive enable. So when this is high, these outputs work and it selects a character ROM, and then when it's high here, it shuts the VRAM off, and vice versa. If this is low, it turns all four of those ROMs off, and then it turns this on, and this is the VRAM. So that's how they select. Likewise, the WRAM is a similar setup here. They have this 74157 quad 2-to-1 muxer, just like the VRAM version, and then this is connected to the MMC3's, positive chip enable for the WRAM, the write enable for the WRAM, and then the WRAM negative chip enable, and then these just run to the RAM chip's control signals. And if this is, and then these are all the same muxer, and then so if this so bit U16 bit 5 controls if the MMC3 WRAM is going to work, and it also controls if the MMC3 controls A17 on the program ROMs, or if A17 comes off of here. And these are the other, this would be like the AN ROMs, A17, and then these others are just U16 bit 0. So what this allows them to do is select any 128K bank using this bit here, because U17 would be for a 256K bank. So that's pretty much how this works. And this is just your stock AN ROM mapper and your stock UN ROM mapper, and this is exactly how it works on the cartridge, so there's no surprises at all there. What I'm kind of surprised at is they could have combined these, because see, this is latching D0, 1, 2, and 4, and this is latching D0, 1, 2, and then nothing. It's just pulled high. So they could have just, they don't even need this chip at all. They can just use this one and then use the 3 bits and get your UN ROM off of D0, 1, and 2. So I don't know why they didn't do that. They could have totally eliminated that, because the read, write, and the CPU chip enables are all connected the same. So those two chips are exactly connected the same. So I don't know why they did that. Maybe they thought maybe they were going to use D3 at one point, but it's actually pulled high on the board, so they can't. So this was just a waste of a chip. That was stupid. Oh yeah, and then these are the registers down here. So I determined what most all these bits do. So this would be, U16 bit 0 is going to be program A17, program A18, and then I'm guessing these 3 are going to be 19, 20, and 21. And see, that's why I've got this set up with the monitor, because I will be able to confirm this. And then, bit 16.5 is the MMC A17 enabled, plus the WRAM, which I already discussed. And then 16.6 is the WRAM control. And then 16.7, I'm not sure what that does yet, so we'll poke that and figure that out. I think this unmaps the 64K EEPROM and maps in the other stuff, so we'll find out. And then 15, it goes to the P. This one goes to that 44-pin device. And we got character A, 18, 19, and 20. And then we got mapper select 0 and 1. And then I don't know this PLD number 6. I don't know what that does. And then this is a no connect. So we've got 1, 2, 3, 4, 5, 6 bits to figure out. So then I will use the monitor in here to figure those out. So from this point, there's not going to be a really whole lot you can see. What I'm going to do is I'm going to simply poke those registers and then figure out which bank shows up here. Okay, so that bit 7 of this is gonna be 5001 hex, which is U16. So it's now high. So I should be able to read back off of these EPROMs in some fashion. And what I'm going to do, I made sure I'm going to write all zeros here and here, and if I write all zeros, that's going to be AN ROM. So now we've selected AN ROM, this chip here, and since I've selected all these, so now if I read 8000 hex, this probe should blink when the EPROM in question is being read. Put that on there. So now I've got a little logic probe on a clip lead. So we got 44, 43, 42. So we got 42 there. So let's see. 44, 43, 42. So it's high right now. So, there we go. So, ROM 18 is our first ROM, and I will dump the data and confirm that, but that's... So, 42 is our first ROM in the list, so now I will write 1, 2, 4. I'll write 4 to 5001 hex. So the probe is no longer pulsing, so now I'm going to say it's going to be U, which is pin 41, that's one down the line. And it sure is. So now I'm going to write 8 in there. And it no longer works. Good. So it should be the next one down the line. And it sure is. Now I'll put 8C in there, or, C. And okay, no longer works. So I'll go to the next one down the line and do it again. No, now it works, yeah. And then I will write 10 in there. And it should be the next one down the line. And it isn't. Interesting. And it isn't, so I'll try 14. Nothing there. 1, 8. 1, 8. So 1, 8 would be 6. Now that's interesting. Yep, and I'm getting data there. Yeah, so it looks like it's so you got 0. Let's see. Oh yeah, 0, 1, 2, 3, 6. So 4, 5, and 7 aren't used. Why they started with 0, 1, 2, 3, and 6, and not 0, 1, 2, 3, and 4, I don't know. Maybe they just thought it'd be better because it may throw somebody off that's trying to reverse engineer it. I don't know. So I've confirmed the banking order. So what I will do, I will dump this data with my device here and see if it matches what I think it should match, and I'm sure it will. So that will confirm the order of these ROMs. So it's confirmed this is ROM 0, 1, 2, and 3 when it comes to those select bits. So when I make the NES file, that is the order that they will be put in the NES file. Then this one will be last, and then this little 64K will be at the end of that probably. So that's how that's all banked up. So now I'll just confirm this last one and make sure there's nothing else in those empty banks, and there wasn't. All I got were zeros. And there is a resistor network here that pulls the 8 data lines to ground, so this board does not actually do open bus because these pull down resistors make sure any unimplemented address reads a 0. So then the other thing I'll do, I'm going to dump the entire address space, and I'm going to figure out exactly where this dip switch is mapped that way. So I got this dip switch set as the first 5 are off, then on, off, on. So I should be reading, I don't know what order they're going to be in. If this is bit 0, we should read, 0. So I should read A0 if this is the high bit, and if this is the high bit, I should read 05. So I'll read A0 or 05, somewhere around 4FFF, if this is indeed the dip switch. Yeah, it looks like the dip switch is readable from 3, 4, 5, 6, 7, 8. It shows up 16 times in memory, 16 bytes apart, so it appears that the dip switch is occupying a whole entire 256 byte bank, but it's only readable in one of the 16 locations, the very last one, and they're reading it at 4FFF. But what's kind of strange is I'm reading F3 is what's coming back. Oh, I guess that would be right, wouldn't it? So these bits must be out of order. So I will click each one of these bits and read the data. So right now, 6 and 8 are on. So I'm going to turn all these off. So now these are all off. So all 8 bits should go high now when I read that. It should read FF. And it is. It's reading FF. So I'll click dip switch 1 on. Still reading FF. Maybe that switch is bad. Oh, now we're reading FE, BE, BC, 9C, 98, 88, and 80. So this dip switch is actually bad right here. I don't know if it's damaged or what, but I'm reading 80 hex. It should read 00 now that all 8 of them are on. Nope, still reading 80. That's interesting. So bit 8 here, it actually goes somewhere. It's actually connected to these parts. So that's kind of unexpected. So this input port, these 7 switches are checked, and this 8th one does something else. I'm not sure what that does, so we'll figure out what that's doing. So after playing around with this, now I know what 5, so now we know that now I know that this is 5001 hex and this is 5002. Now we know that these 3 bits are indeed the A19, 20, and 21, and we figured out which order they're in. And we know that this bit here disables our 64K ROM in the 8000 to FFFF range is what that's doing. So what I'll do is I'll turn this on and off and I'll dump twice, and I'll be able to figure out if that's all it's doing or if it leaves anything else on. So it looks like with that bit set, the only thing that is accessible from the 64K EEPROM is 5000 hex to 5FFF hex, and it's actually 5010 hex because 5000 through 5000F are actually registers in this, and then these 2 chips decode that. So this appears to decode some of the lower address lines, this decodes some of the upper ones, and I'm not quite sure how they work together exactly, the division of labor, but it really doesn't matter because as far as I'm concerned, these are acting as one unit, and I'm actually probing the board to figure out what they're doing versus trying to actually reverse engineer these, which, I mean, yeah, it can be done, but this way is so much faster, and I know exactly what's happening because I can actually poke these registers and see what updates. So I kind of like that idea better. We know now what all 4 of these connections do. So now I'm kind of curious what this does right here, 15.6, and it goes to that 44-pin PLD pin number 6. And I don't know what this does. So that'll be the next thing to figure out, to see if this actually does anything or not. Okay, got the video turned on here, so we're seeing that's character RAM right there. And the reason I turned this on, I'm gonna I saw those other 2 bits, and this appears to control some of the character enabling or something. I'm not sure what. So I got to turn the VRAM off, and I'll do that by setting the bit, which tells it to use the character ROMs instead of that VRAM. There, so I wrote C0, and sure enough, we got, oh, that's funny. Logic probe's picking up the static when I touch the monitor. Anyway, so, our character ROM is now enabled, just like my documentation says it should be. And so by writing 5002 bits 1 and 2, I should be able to select the character bank. So there's 0. So now I'll write 2 in there. Yep. And then 4. And then 6. And nothing happened. Unless it's the same character data in there. Oh yeah, that makes sense because that is the 27010. So yeah, that makes perfect sense actually. So that's not actually selecting. Now that's selecting character A18, 19, and 20. So I'm guessing 5002 hex bit 0 is going to be character A17. Yeah, I'm not sure how character A17 is connected. 18 and 19 are connected to the latch here. But I'm not sure where 17 is connected. There is a bit which would be A17. And it's connected into this chip here, but it doesn't appear to do anything when I write to that bit. So I'm not sure. I may actually have to probe this and figure out where A17 is connected. Here, let's see. Oh, there it is. Pin 37 appears to be A17 of this thing. So pin 37. And guess what? Pin 37 I have as a no connect, but that's really A17. Okay, so now we know that that's A17. So now the next step is to figure out how to toggle that pin. So I have a feeling we're going to find it either 5000 hex or that bit in 5001, something like that is going to control that. And I'm not sure who gets to control A17 because I don't think an MMC1 can control 256K of character, and MMC3 sure can, but I don't think it's hooked up on here. I looked on the board and it does not appear it's hooked up, but I may try anyway just to make sure. Yeah, so the only thing with a character A17 would be the MMC3. Nothing else has a character A17. So I'm guessing it's pin 10 on here. There are 3 pins on this chip that I couldn't figure out what they did because on my other board they're not hooked up. So there's pin, hey, pin 10 appears to actually connect somewhere. 4, 5, 6, 7, 8, 9, 10. Ah. Looks like pin 43. So 43 is MMC A17. Okay, so that's 2 more pins of this chip identified. So that must mean there is some way to use this bit out of here to control A17. So now I have to figure out how that's being done, and I'm sure it's probably writing to 5000 or 5003 hex if I had to guess. And going by the pin out of this chip only accepts data line 0. So that means only D0 or bit 0 matters. So all I have to write is 0 or 1 to each of the registers in the address space to see if A17 all of a sudden starts to work, which is what I'm guessing is going to happen. Okay, so we're back in character ROM mode. So now what I'm going to do, I'm going to write to 5002, I'm going to write 0 there. But I am going to check something else. Okay, so this bit here is reading high. It's kind of hard to see that on the logic probe there, but the logic probe's reading a high. And this is the audio enable bit, so it's high right now. So I'm going to write to a couple of these addresses and see if I can make that change back to low. And I did. So 5000 hex controls the audio enable. So if you write 0 to 5000 hex, it will shut the audio off and turn the speaker off, because it'll cut the audio going to that amplifier. So then if you write 5000 and or you write 1 to 5000, it will turn the audio back on. So I can turn the audio back on. Simple as that. So now 5000, we know what it does. 5001, 5002, and then 5003 through 5000F, I'm not sure what they do. They're decoded, but they may not actually do anything. And yes, that's the chair again. So actually, what I'm going to do, since I've written 1 to all of those addresses, I'm going to see if bit 17 is reading high. No, it's low, okay. So I'm wondering if bit 6 turns A17 on and off. So to test out that theory, I'll have to write 4 in there. So I'll write, say, 42. I'll write 40. So there's 40. Now I'll write 41, which should select A17. So here's 41. Aha, and it works. So now we know what these last 2 bits do. One of them enables A17, and the other is A17. So if bit 15.6 is low, then the MMC3 has control of it, character A17. If it's high, then 5002 hex has control of it. So now we've reverse engineered 3 registers that control audio, and then character, program, mapper, and all that other fun stuff. So the only thing left is to see if there's anything I've missed. And the only thing I can see I've missed that has not been addressed is what this does. So I got to map. Actually, here what I'll do, I'll map these dip switches really fast. So that's the mapping. Basically what they've done, the bits are scrambled because they've just run them directly into this 244, which is 2 4-bit tri-state buffers. And so the ordering looks like 0, 1, so it's 0, 1, 2, 3, 4, 5, 6, and then 7 connects to these resistors in some fashion that I'm got to figure out now. So that's all of that fun stuff. Okay, so the registers are indeed mapped from 5000 to 50FF, and there are 16 slots, but it looks like only 3 of them are occupied. So slot 0 is the audio enabled, slot 1 is U15, and slot 2 is U16, and slots 2 through F are just not used. So that's all the hardware on this entire board has now been figured out, except what this dip switch does, and what these resistors are doing, and what bit 7 of the 244 is doing. So that'll be the very last step. And then this hardware will be all 100% documented, and I will actually write up a document on how this works. I will make an NES ROM image, and I will run it on this FPGA board, and we'll be able to actually play it on this monitor coming from my FPGA without needing this board at all. So I don't know, that switch may not be hooked up to anything. It may just be floating in the breeze there. So to confirm that that switch is not hooked up, I'm going to shine a light through the board and look. That will let me actually look underneath the dip switch, and I'll be able to actually see if there's actually a route going under there or not. And there isn't. So there is no route on the top of the board connecting that dip switch, and there is no route on the bottom. So that dip switch is not being used. So switch 1 is not hooked up at all. It's just floating in the breeze. Now, knowing that, we will see where bit 7 of this chip is going, because that seems kind of interesting. Okay, it's going to R15 here, whatever R15 is doing. There's a capacitor here. Oh, this is kind of strange. So bit 7 appears to just connect between a capacitor and a resistor? Why would they do that? Oh, it actually goes somewhere else. Okay. I'd be very surprised if it didn't. Ah, okay. So, what this is doing, this is the start button here. The start button is wired two places. It's wired to the 4021 like usual, I believe. Maybe not. Oh. Let's see. Oh, it isn't. Hey, that's very interesting. Okay, what they have done is this is the button. This would be where the start button connects on your NES controller. So what happens is the way they've hacked the games is you can't hit start when it's showing the track screens. You can't hit start to start the game because there's no start button. The start button's not hooked up on these 4021s. So here's where the start button connects, and it actually connects to bit 7 of the dip switch doodad. There it is, right there. And then the other side, connects to the 244. So bit 7 of 4FFF is actually the coin in signal, and that's normally where start would be connected. Okay, so that explains that. So this board is now 100% reverse engineered, and I'll test one more minor thing before I remove these wires, and that is when you turn off the control EEPROM, or when you turn the control EEPROM on, how much of it is actually mapped into memory. I'm guessing it's going to be 6,000 through FFFF, but it may only be 8,000 through FFFF. So that is why I'm going to just test that very quickly here. Okay, yeah, it looks like when this ROM is turned on, only 8,000 to FFFF are visible, and when this ROM is turned off, it's just these ROMs here through all the mapper mess. So when this ROM is on, all the mapper mess is disabled, and it's just this 32K, and this holds, it looks like patches for the games, for as far as I could tell. So this board is now reverse engineered. I will take this stuff off. So now that's my little debugger here. Yeah, this thing worked excellent. I'm glad I built this, so I'll get to use this a bunch more, I bet, on other projects. So now the board's back the way it was. I'll plug my EEPROM in, and see, this way I didn't really have to do any damage to the board to reverse engineer it. All I had to do was remove that EEPROM and solder two wires on. So I think that was a pretty good deal. So now, moment of truth, and sure enough, it works great. Super game, Mega Type 3. So now with that capacitor removed from the board, the video quality is as good as it would be coming out of a modified NES. So I'm pretty happy with that. There's a little bit of jail barring, but what do you expect? It's a pirate PPU, and my ground is clicked over here instead of really where it should be, which is closer to the chip, and yeah, who cares? It's working. I think it's kind of funny that the graphics are kind of screwy, and I'm pretty sure that's because they took the game name out. Notice a lot of the games are hacked like this, where they've taken the name out, and they've just done like a really horrible job of it. I don't know why they did such a crappy job. I mean, they could have just left it in. Hell, everybody knows what game it is. It's pirated. Come on. Okay, so here's my audio. So So I should be able to probe around and find my audio signal. I'm guessing it's going to be like right here. Let's see. Yep, so there's the noise in the triangle. And then there's the squares. And there it is all together. So that's the squares, noise, and triangle. All together now. So I can cheat here and look on, whoops, on the bottom of the board here. Oh, it's going through the pot. Oh yeah, well that makes sense. It's coming out really, really quiet, so crank up that resistance. There we go. So there's the audio coming out of the pot. So I'm guessing that's going to come in here. These pins. And see, it's coming out of pin 2 there. So there's our audio. I want some 60 hertz for me. Ooh. No, 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 no. I want some 60 hertz for me touching that signal there. So now if I reset this and I put my audio probe right here, should be able to hear some of the games. If the games have an intro, we should be able to hear them. So pin 2's got our audio, but pin 1 now is cut off. So that means the audio now is shut off because it's in a track mode, so that way that noise doesn't come out of the machine while it's waiting for money to be installed. But see, there's the audio. So pin 3 must be sitting low now because this is a 4066, which is an analog switch. Interestingly, it connects to pin 13. Oh yeah, that is right. Pin 13 is indeed the enable for pins 1 and 2 of this chip. Yes, that is right. So, yes, that is exactly what that is. That is indeed the audio enable pin right there. So, that is what that does. So, 5000 hex is indeed our audio enable. Also, thanks for watching part 2. Part 3 will come up in probably a couple days. I'll make an NES file, get my FPGA to play it, and then I'll release the documentation and probably the ROM if anybody else wants to play with it. And I guess that's pretty much it. Hope you like it, and thanks for watching.